So I'm going to show you the old way first. So the way that YT used to regard particles is in a way that that did its best to minimize the distinction in handling data between the grid-based data sets and the particle-based data sets. And so what it would do is it would read in all the particles, and then it would construct an octree mesh to index them, and then it would use that mesh for visualization purposes. So it would deposit all the particles onto the mesh. And so when you loaded a data set, and this is me loading a data set in YT3, what it would do is it would read the data set in, and then as soon as you started to access any data, so let's say that I do ds.r, density, or gas density, you'd see that it would allocate for this many particles, it would identify this many octs, and what it would do is it would read in all of the particles, it as few as at a time as it could. It would turn them all into Morton index integers. It would sort those integers, and then it would do this really fun prefix-based guessing in order to figure out the depth of a given octree at any given point. Um, this was a really, really fun algorithm to implement and to use and to optimize, but it's just not great. And in fact, the reason that it's not great is that it's essentially taking the SPH particles and trying to turn them into something they're not, which is mesh particles. And so if we were to do something like a projection plot of this data set, um, and we were to look at a projection plot, it would kind of look like a good data set, but on the other hand, it would also show all of these different artifacts from the way that the data was constructed. You'll see eventually that when this comes up, that what it does is it embeds this meshing into the output. Not only that, but it's really slow, as you can see here, because what it's doing is it's constructing this octree, then it's meshing it, and it's doing this search over all the different cells, and it ultimately was a really uh, fun and exciting experiment, but it was unfortunately not the right way to go. And you'll see that here. Now, it does have some advantages, like if I zoom in here, that process is essentially instantaneous. But you start to see the meshing artifacts. Like right here, we've got low resolution areas that are enclosing high resolution particles, and it's just not that great. Um, so what we've done over the last year or so is we've redone the entire particle infrastructure to get around this problem. Or actually not in the last year, the last several years. Uh, this process, what we call this, has been the demeshioning. Um, we came up with this name around the time Stranger Things 1 was put out, and so we had this really cool logo that was in the Stranger Things style that said the demeshioning. It was supposed to sound very sinister. But what the ultimate idea behind the demeshioning was that rather than apparently this looks just like the particle things from The Expanse, someone says, or Medican says. But what we ended up doing was we changed the way that we index the data on disk, and in doing so, we eliminated this notion of a global mesh. So instead of trying to square peg particles into the round hole of meshes, what we now do is we conduct this completely differently. The other thing that this brings with it is it brings with it the ability to do much more efficient reluctant loading of data. So the way that YT3 handles particles is it handles them via uh, uh, this octree, but that octree also doesn't lend itself well in its implementation for reluctant loading. So if I load data from this region, I mostly have to load it from the entire data set. So in YT4, we've redone this infrastructure from the ground up using something called bitmap indexing. I'm going to show you a couple diagrams of what the bitmap indexing looks like. You can imagine this text and the bitmap indexing implementation was all written by Megan Lang, who's a research scientist here at Illinois. You can imagine that oftentimes codes will have different organizational schemes for particles. You might have one where it just randomly deposits particles into different files. It might be sliced. This is actually how, if I'm remembering correctly, the Friends of Friends algorithm from Gadget outputs data. Then sometimes it, will do Morton indexing, and then you'll often get other mechanisms like the Hilbert curve where you preserve some spatial locality. And so in the Morton and the Hilbert curve indexing, you get some type of spatial locality where there's a rough correspondence between things being close together in space and things being close together in their numerical value along a space filling curve. So what yT does is we want to be able to select a small subset of regions, and then in each one of these diagrams, a different color represents a different file on disk. If we're just selecting a sphere, we want to be able to know which files we have to read in order to get the particles from that file. And if it's in this mechanism in random, you might have to hit 4, in slice you might have to hit 2, and some of the space filling curves you can reduce that. But what we want to do is we want to be able to index them. So what yT does in yT4 is it constructs 2 levels of indexing: a coarse indexing, where at some resolution we mark different sections as being contained in different files, and then anywhere that a file collides with another file, we apply a second level of refined collisions. So we have this multi-level sparse indexing. So the ultimate result of this is that we now have a mechanism for, and I think that's pretty much all I want to do about the theoretical background, but we have a mechanism so that if we want to read some subset, we can minimize the number of files that we have to touch in order to read that subset, and we can maximize the speed with which we're able to identify which files those are. So instead of getting a result like this, where you can clearly see the mesh embedded, and there are all these different free parameters, like for instance, you can, in yT3, you can change things like the number of zones per oct leaf node, and you can change the number of particles that cause refinement. We now have a completely parameter-free mechanism. So if you are running yT4, you can open it up and you can import yT, and we can load sample snapshot 033. And I think I showed this a little bit yesterday, this specific file. And this is an OWLS data set. And if we look at the parameters, you'll see it's got stuff like the box size, num files per snapshot, which we'll take a look at in just a minute, number of particles, and this grabs it right from the very first file, number of particles total, and so on and so forth. But the main upshot here is that we can do a projection plot along the same axis, and we can look at that projection. And you'll see that here it loads a particle index. So this is a binary on-disk particle index. And it's also considerably faster, both for reading the data and generating the ultimate visualization. Now, one of the downsides to
Hey,
not
Matt,
regarding the, yeah.
we have a question from Ari.
Oh yeah, hi Ari. Thank you for interrupting me. I have a tendency to get going.
Oh, it's good. Just a quick clarity, and this may not actually matter as far as what's been implemented in front end so far, but is a particle in this context anything that's not on a Cartesian grid?
That's a very good question. The answer is sort of. Anything that is infinitesimally spaced, yes.
Okay,
So
so a non-struct, but a non-Cartesian grid would still be loaded in the grid format.
that's right. So if it's logically Cartesian, it would be loaded. So if it's logically Cartesian, but not necessarily geometrically Cartesian, it would be loaded as a grid, not as particles. If it is an unstructured grid where the vertices are given, we have unstructured mesh loaders that can do higher order internal interpolation.
Thank you.
So but the upshot for things like AREPO and moving mesh is that typically it's better to load them as discrete points, and then use a different kernel for the visualization process.
Thanks, that's great.
Yeah. So if we just compare the difference in the two plots, you'll see this one is much more attractive. This new one is much more attractive. We also have, as by virtue of the fact that we are now regarding these as particles and we're applying either scatter or gather, whichever is the good one, methods for the SPH smoothing kernel, we get much higher apparent resolution. So the simulations will overall, the visualizations will look a lot better. And if we zoom in by the same factor and we compare the resultant images, you'll see that as well. Now, one thing I want to note is that because we aren't meshing this at any point, operations like zoom, which are essentially free for anything that's been meshed in YT, take a lot longer because it has to construct the fixed resolution buffer completely again. Now, this may not show up over here, so what I'm going to do is I'm going to copy and paste these two images into the Slack channel real quick. So hold on, let me make sure that, and
Matt, you can also, I think, drag one of the tabs to put the two notebooks side by side.
oh, you're right. There we go. Thank you. So I will copy and paste both of these here, and so just so that you can see them without any zoom compression. Now, the other thing that this also means is that we now have, since everything is now particle first, that means that if we select something here and we do gas density, it's much, much faster because it's not meshing anything. And this refers explicitly back to the underlying particle shapes, whereas here in the old version of YT, it deposits everything onto a mesh and then returns that value. So in general, and I don't want to belabor this too much, but in general, the new version of YT that we're running here and that we're trying very hard to get out the door is much truer to the underlying data structures than rather than the old version. And in fact, here let's do YT projection plot DSX density center equals max. So it's a little bit, it's a bit slower for generating the visualizations after you've generated them once, but it's much faster for overall accessing of data and selecting of data and so on. So the next thing that I'm going to get into, oh, side by side works well, yeah. So the next thing that I want to show, oh, and I think I may have asked too much of it just now, is I want to talk a little bit about different data file formats that tend to show up with things like Gadget. So one thing that happens very often with particle data sets, because they're often stored in in binary formats and so on, is that they often have additional fields that are output. So for front ends like Tipsy and Changa and so on, we have a way of detecting a lot of those fields. For Gadget, it's a little bit trickier because oftentimes the fields are appended to the very end. So for instance, we've seen situations where in Gadget there are, a whole bunch of, if they're using the Gadget binary format, sometimes people will put out additional additional fields like metallicity or some stellar age or something like that. So when we load particles or when we load Gadget data file format specifically, you can specify the fields that are output. So yT by default knows about the coordinates fields, the velocities, the particle IDs, the mass, and it knows that internal energy is only for gas, density is only for gas, and smoothing length is only for gas. But oftentimes you'll have additional things like, for instance, in the halo particles, you might have metallicity. And so yT allows you to specify additional field specifications. So here we've added on coordinates, or we've got coordinates, but we're all velocities, particle IDs, which exist for all the particle types. But then we also have metallicity, which only exists for halos, and then internal energy, density, and smoothing length, which only exist for the gas particles. So here we go. Now what's happening here is you can see at the boundary here, we don't have periodic boundary conditions turned on, but if we zoom in by a factor of 10, this is what it looks like in the old style, and then in the new style, we'll see it in just a moment. And again, all of these things, we're working pretty hard on optimizing this to make it a little bit, faster and better. We can zoom in again, see if we can start to really draw out the differences here. Well, I guess it's not quite as staggering of a difference as I had been hoping, but you can see the differences here. For instance, in the new version, we're actually picking up some of the satellites that don't show up in this one because they're under resolved in the octree. So in terms of other functionality, and here, I'm going to save this and I'm going to close the old one. The functionality that we use throughout other areas of yT is all replicated and accessible here. So I'm not going to show the phase plots because those are going to be covered a little bit tomorrow. But we can do things like ds.sphere, and we'll center this one at the center of the domain, and then we'll use a special unit called unitary here. So I think I've talked about units in the past, but yT has a couple special ones, including unitary. The unitary unit is for any time that you want with respect to the entire domain. So here, this is 0.1 in unitary, which means scaled to the largest dimension of our domain. So in that case, I think it's 25. So this should be a sphere with radius of 2.5. Yep. And so if we access things like the gas density, this works the same way that that it would work in any mesh-based code, where it reads all the particles that are within the radius of our or within the radius of the sphere. Now, one thing that I think might be worth mentioning is that So if we look at the radius of each one of these, yeah, it's just gas X, gas Y, gas Z, sorry. So we get really small quantities for the min. So let's do in units code length. You'll notice that the maximum radius is actually greater than the radius of the sphere. So for n-body particles, they should all be completely enclosed. But here, our max minus the code length also includes the smoothing length. So when we select a sphere inside an SPH, inside a set of SPH particles, it includes particles that are, if they are SPH, it includes particles that would be inside the sphere. So if we look at HSML is SP gas smoothing length. And we do NP argmax R. When we look at HSML max R end, you'll see that here, the smoothing length of our maximum radius particle puts it so that the smoothing length minus, or the radius minus the smoothing length is still within our sphere. So that's something that's important to recognize. And this becomes particularly important because if we were to do a projection, so let's say we've got our sphere and we do our, we integrate gas density along the x-axis. We want our sphere to, or our sphere will include particles that are outside of our value. So if we create this P and we plot P, we then plot, let's annotate on that. Annotate circle, which I think Mike showed us earlier. Did I assign it to P? Oh, annotate sphere. So a sphere of radius, sp.radius. So you can see that even though we are selecting only the region that's inside the sphere, because we want to be able to have a closed SPH kernel, we include some particles that are located outside of the sphere because their smoothing length puts them inside of the sphere. So that's something to be aware of with the way that the SPH in YT4 works. But it's not really a problem in the sense that it's just something to be aware of. So if you do things like region selection and then doing a profile or a phase plot, it will include particles that contribute to but are not strictly included inside that object. So the next thing that I want to talk about are particle unions.
Before I think you move on, sorry, Matt, we
Yeah.
have a couple hands,
Oh, my
including mine.
goodness.
I'm not allowed to raise my hand as host, so
Oh, my
that's why I
goodness.
jumped in. But I think I was the last one, so I think Ari's actually first.
Okay. Hi, Ari.
Hi, Matt. I have to hold a baby that's floating away here, but just a quick question. So, but on that projection plot, the area outside the circle would not be correct because it's not using particles that contribute to that area, only the ones that we're using in the
That's
circle.
right.
So
That's
is there an easy way to mask the contribution outside the circle?
That's a really good question. The answer right now is no, but the answer should be yes.
Okay.
So actually, Ari, as long as you're here, I'm going to go ahead and file that as an issue actually, because I think that's something that we at least need to track. And it was something that had not occurred to me. Masking projections and slices from data objects in SPH. At present here, and I'm going to include this image. Oh, here, you know what? You can watch me fill out the issue actually.
Cool.
Did that show up?
Yeah.
Yeah.
Okay. At present, including using a sphere or other region for a projection in SPH and a dimensioning.
I think with this, we'll be one away from having 2,500.
Ooh.
It seems like that deserves cake or something.
Mhm.
I'm going to assign myself, and then I'm going to add some labels because we've got a dimensioning label.
Ooh.
Live labeling. This is so cool.
I know.
And can I just ask a follow-up on that?
Yeah.
And so if you had chosen a particle whose type was different, like a star particle, then it would take only the location, or would take the gravitational softening as another?
It would not take the gravitational softening.
Okay. So everything else besides SPH is considered to be exactly at this point.
Yes.
Okay.
Now that's not something that's like, it's not something that is a hard requirement in the code. It's just how it is at present. So in principle, the way that we augmented it for the SPH visualization could be augmented to include gravitational softening for stars and things like that. But at present, it is not.
Okay, thanks.
Mm-hmm.
Okay, I think our next question, unless Ari, do you have a follow-up? Or are you good? Okay, so the next question is actually from Mike.
Hi, Mike.
Hi, Matt. I actually was going to ask exactly what Ari asked as his first question about whether the plot's valid outside of the circle. So
got it.
Oh, wait a minute. I missed the answer to that question. It
It's
is
not.
valid? It's not.
No,
Okay.
it's not.
Okay. And so is that going to run, are we going to run into that same problem with like phase plot?
Kind of. Yes.
Okay. So we probably, I don't know.
Yes.
So if they can be masked, I don't know. In my head, it feels like it's easier to mask them out of a projection than it is out of a phase plot, but maybe that's not true
Well,
in
so
like how YT works.
so actually, so let me think about this for a second, because it's also, let me actually, and I should look at the source code, because so YT has two different methods of defining a selection operator, sort of the sloppy and the strict. And I don't like that term sloppy, so let's just say normal and, or let's say forgiving and
Relaxed.
strict. Yeah,
Right.
relaxed and strict. And so in the strict method, it would be anything whose infinitesimally defined central point is within the object. And then in the relaxed, it would be anything that would contribute to it. And so let me see if we're using that in the so let me actually, I'm gonna go back to the bug report that I just filed. And I'm going to make a note. It's possible that this could be related. Oh, you know what? I'm gonna make a new issue. I'll get 2,500.
That's why you're doing it.
It is actually.
So it's a super good reason. So
Clarify. And
You get a YT
rigor.
sticker. Everybody gets a YT sticker.
yeah.
Let's see. There's delineate usage of strict versus non-select. Delineate. Strict selection may be appropriate for most data objects, especially as would be fed into a phase plot or profile plot.
By the way, Matt, I think it's awesome that you're live streaming your issue filing. So this is no, seriously, this is something we're going to talk about tomorrow. So
well,
it's
thank you.
nice to see.
Yeah. So just so that I totally understand what the idea is, because, right, so you need to think about everything in the kernel in order to get the appropriate density. So for any of those plots, I would still need to think about those, but I just need to kind of scratch them out of my data in the final plotting or profiling or whatever.
Yes.
Anything that's centered there.
Yes.
But still use them for everything that's centered in the circle.
Yes.
Cool. That was my question too. So I think,
okay.
Unless anybody else had a hand, that's it.
Yeah, and I don't think I'm speaking out of school, out of turn when I say this, but the visualization of, so the way that we manage the visualizations of mesh data is much more rigorous in terms of like tracking the objects that go into them and so on. And the way that we manage the actual objects that go into the visualizations of SPH has yet to be sort of made rigorous. And that was actually something that Nathan Goldbaum put a lot of hard work into constructing the infrastructure for visualizing SPH data, and then he moved on to other projects, and I know that he was not completely satisfied with where this was left, and we haven't picked that back up yet, but we hope to. Does anyone have any additional questions?
There's no new hands, so I think you
Okay.
can go.
Okay. So what I want to cover next is I want to cover a little bit about particle filtering and particle unions are actually really hard to cover, but I will try to. So oftentimes when we're dealing with particles, we want to be able to filter out and only look at particular types. Now, believe it or not, this is much more common with grid codes than with particle codes, just because grid codes tend not to do as good of a job with identifying different particle types. And that's a value judgment. I know I shouldn't make that value judgment, but the way that we often think about this is we think about this with if you have multiple different particle types that are separated just by like an index or something. So let's take a look inside our data set, and I want to look at the particle types that we have. So if we actually look at our data set and we look at particle types, you'll see that we have part type 4, part type 0, part type 1, all, and n-body. So these are all the different particle types that exist on disk, or that exist inside yT's memory. Particle types raw are just the ones that exist on disk. And we can also look at things like particle unions. So here we have two different particle unions that get defined by default. There's the all particle union and the n-body particle union. We can also come up with particle filterings. So let's take a look at our, let's see, did we define DD? No. So let's DD equals DS dot all data. And then let's take a look at our, let's see, DD part type. Does anybody remember, is in Gadget, is it part type 4 that's usually gas? Oh, you know what? ds.fields.part type 4. Let's see. Oh yeah, this has got a lot. So let's do we'll do profile of velocity magnitude with respect to particle mass. Weight field equals none. Every time I do this on live, it messes up, so I'm sorry. Let's say that I want to filter my particle. So this is my mass distribution of particles as a function of velocity for my gas particles. So I've got my velocity magnitude here, and you can see that I've got some particles that are way higher, way higher velocity than others. and I've got this lower mass down here. So here, or I've got a whole bunch of sorry, I'm getting a little bit mush mouthed. Let me try to.
Matt, I don't know if anybody mentioned what profile plots do yet.
I don't think anyone did.
Do you want to maybe just mention that?
Is Stephanie going to talk about that today?
I was just jumping straight to phase plot. I was not
Okay.
going to deal with profiles.
Yeah, so I'll talk about this then. So what there's an object on there's a function, or well, there's a function that hangs off all data objects called profile, and if you supply it one field and then a second field, what it does is it will do essentially the probability distribution function with this as your independent variable and this as your dependent variable. You can weight it, in which case you get an average, which doesn't make as much sense for things like mass, or you can specify the weight field equals none, in which case you get a sum inside the bins. And so you can see this is how much mass in particles in gas there is between 10 to the 7 and 2 times 10 to the 7 centimeters per second. And so what I'm going to do here is I'm going to identify that I only want to look at particles that are above 10 to the 7 in velocity magnitude. So what I'm going to do is I'm going to define a function, def high velocity. And this takes a particle filter object and data, and we almost never access the particle filter object. Well, that's not true. We do access the particle filter object, but usually just for one specific thing. So let's say Vx is equal to data, and so we'll say p type equals p filter dot filtered type. Particle velocity x, Vy is data p type particle velocity y, Vz is data p type particle velocity z. Vmag is Vx squared plus Vy squared plus Vz squared, and the square root of that. And what we return from this is we return a mask, where that mask is all of the ones that we want to accept. So we can return wherever Vmag is greater than 1e7 times yt.units.cm divided by yt.units.second. So we want to have we want this to be unitful. So now that we have that function, we can do yt.add particle filter. I'm sorry, we can do ds.add particle filter. High velocity. Our function is equal to high velocity. The filtered type is gas, and it requires particle velocity x sorry, I had this.
I think you might not need all those particles now that
I think you're right.
that's the change, because before you had to distinguish particle type and gas type.
Yeah, you're right. So now we have a particle filter that's called high velocity, and now we can add that to our data set. Okay, and it worked. So now, let's say dd equals ds.all data. Now let's take a look at what we can get if we do high velocity and density. We get back that many particles. And so if we look at dd.high velocity and we look at velocity magnitude, you'll see our minimum is just over 10 to the 7 centimeters per second. So now why don't we do something like this? P equals yt dot projection plot. On ds, we'll go to x, and this time we want our field or our particle type to be high velocity and our field to be density. And so what this should give us is it should give us a projection of the density where it only accepts the particles that are high velocity. So greater than 10 to the 7 particles per cc. And so you'll see now, once again, we've got some empty regions because these are probably just only low velocity particles in this area. But the rest of our system only shows our high velocity particles. And in fact, let's do another profile here, where this time instead of gas velocity magnitude, see our velocity magnitude starts here now. So, oh, looks like I've got an at. Yes, Stephanie, you can in fact see which particles make up those. So Stephanie asks if you can see which particle types make up all and n body. So you can access that if you look at this particle union. So all P union is equal to that. And it has subtypes.
Cool.
Yeah.
Cool. Since you've paused for a second, can I ask another question?
Yeah.
So I'm a huge fan, as you may or may not know if you follow me on YT users questions, of cut region.
Yeah.
Why are you, it feels like this is a really complicated way to do a cut region.
So that's a good question. It is a bit more of a complicated way to do a cut region. The reason that we do this is because we can. So part of it is that if we do it this way, we can, well.
Sorry, while Matt thinks for a second, let me just let everybody else know, just in case you don't know, cut region is like ds.r, where ds.r was, we were doing some sort of like position space, and cut region lets me cut on other things. Like I should be able to do a cut region where velocity underscore magnitude is greater than 1e7. And then that would only give me those things. And so then instead of like using my region, you know, that was defined as a box or something, I could use a region defined as just those particles. So sorry. Okay.
I will say that you could do this with cut regions. Defining a separate particle type allows you to distinguish between things that the code might that the code might distinguish between. And our fiducial example is actually for ENSO data. So ENSO data, for instance, this is and when I say fiducial example, I just want to be very clear that this is that this is because of a not quite shortcoming, but kind of shortcoming in ENSO that we do this. So the example that's in the docs is actually this. So in ENSO, star particles have an attribute field associated with them that's particle type. And so we want to have our star particles constructed in this way. The other thing that this lets us do by constructing a different type is it means that we can do things, and I'm not going to do this now because I would mess it up without reading the documentation, but you can do things like constructing information about the nearest approach between different objects. So for instance, if I define if I want to find out what is the nearest high metallicity particle to some, low or to like a massive black hole particle or something like that in a simulation, I could do that with particle union or with particle filters, because I can do computation of nearest values between particle types, but I couldn't do that with cut regions
I see.
because they're the distinction because the gas comma density in a cut region is indistinguishable to YT's machinery from the gas comma density in a different cut region, even if the cut region itself is defined based on the gas density values.
Yeah. Okay. Thanks.
Mm-hmm.
You have another question from Ari.
Hi, Ari. Oh, he's physically raising his hand.
It's a double system, but I was just going to continue on that with Persephone's
Yeah.
question. Actually, another advantage is that one way I use this a lot is if you want to rename, like if you're talking about many different codes and you want to, you can then define your particle filters, which will be different class of different things, and all have the same name, and then continue the rest of your code with everything defined that way. So it can make it very readable
Yeah.
way of dealing with things too.
Yeah.
Okay, and so that brings us to 11:30. I'm going to, or to 11:30 my time, but to our scheduled break time. I'm going to hang out for half an hour here, and we can talk about any other stuff with particles and so on. I know that particles are a big piece of interest for folks, and so I want to make sure that we talk through everything that's of interest. So I'll be around for the next little while, but I think that we can conclude the formal presentation at the moment, if that's okay.